Welcome, welcome to the first half of lecture 17, scheduled for the end of the 6th week of our 8-week summer course on computer algorithms. In this lecture, we close off the chapter on network flow, or the chapter on the application of iterative algorithms to solve a diverse set of problems, essentially by the same algorithm. So in this lecture, we consider three different problems: computing disjoint paths and graph, designing surveys, customer surveys, and then we look at airline scheduling. So these are three different problems. They can be solved in polynomial time by the same algorithm. Okay, let's start with disjoint paths and graphs. When we think of flow, we can think of traffic, actual traffic, and we are given a graph or a network, and the edges represent the roads, and the vertices are the intersections, so where two roads meet each other. Then we say that two paths in a graph are edge-disjoint if they do not share an edge. So um, we can consider any two nodes, any two intersection points in our road network and ask how many different disjoint ways are there to travel from one to the other node. So that's the problem we consider. So this is the edge disjoint path. And in some sense, this gives you the way to plan if you are a city planner and you have to think about the repairs to roads. You would like to make sure that the optimal number of ways to get from two important points in your city are not disrupted too much. Okay, how are we going to solve this? Well, we're going to solve this by means of the Ford-Fulkerson algorithm, and we have to prepare the input for this Ford-Fulkerson algorithm. So any two vertices that we consider, one of them is considered the source and the other one is considered a sink. So we consider here also a directed graph. The problem in generality works for any graph, but we will focus on directed graphs. So we then define the flow network, which we write as G prime, as the network which has two additional vertices, or I'm sorry, where actually the two vertices that we are interested in computing all the disjoint edge paths, as the source and the sink. And we set on all the edges the capacity 1. So then the first lemma is that if we have k edge disjoint paths in the original graph, then on the graph with G prime with the edge capacities equal to 1, we have a maximum flow of at least k. So we are defining the input for the flow problem, for the maximum flow problem. And first, if we have a solution, what does it mean for the flow? So that's the easier question that we will answer first. It's important in solving a problem to make sense of the questions. So what is edge disjoint paths in one problem becomes flow in another problem. Do they line up? And in one direction it works at least. So if we have edge disjoint paths, we have k of them, then we can define a flow as follows. So for all the paths, so we have k of them, for all the edges in these paths, we define a flow of 1. And for all the other edges that are not contained in any of the path, we have a flow of 0. So that defines for any set of k edge disjoint paths from source to sink, this defines very obviously, clearly, unambiguously a flow. It is a flow, it satisfies the capacity conditions and also the conservation conditions. The capacity conditions, the capacities were 1, so we stay below 1 or equal to 1. And what will go in out of any vertex will go out. That's also can be seen by these paths. Okay, so that then obviously if we count, for example, the number of outgoing edges from the source, then obviously we have k paths. We have a flow of k, and all our paths are reaching the sink, and we have k of them. So the value of the flow is k. So the fact that we have defined a flow network or a flow with 0 and 1 suggests that we are counting things. So we are counting paths. Okay, so one direction works. We have also the other one. So we can say that if we have a 0-1 flow of value capital F, that will be maximum as computed by the Ford-Fulkerson algorithm, then we do have capital F as edge disjoint paths. So this lemma is a little bit longer to prove, but in some sense more interesting from our perspective as it leads to an algorithm. So, but what this second lemma implies is that there is a one-to-one correspondence between the two problems. So the problem we know to solve already by the Ford-Fulkerson algorithm, the maximum flow problem in our network flow, and that's equivalent to solving the edge disjoint paths problem in both directions. So this is an if and only if problem. If you have a good algorithm for solving the network flow, and we do, 2 lectures ago, lecture 15, dealt entirely with the Ford-Fulkerson algorithm, then actually we can solve the edge disjoint paths problem. Okay, so there's one issue here. We have to figure out how to get from the flow into our edge disjoint paths. So if we have the edge disjoint paths, we can define a flow. That was the first lemma. But now the second lemma says that if you have flow of a certain value, then you also have that many edge disjoint paths. Now, how do you compute them? So that's actually the point in this second lemma. So we will do two things. The lemma will be proven, but at the same time, we will actually also give an algorithm. So the path decomposition procedure. Okay, so here is the statement of the lemma again. If we have a 0-1 flow of value capital F, then this capital F is actually the number of edge disjoint paths. So we will compute these paths, but also prove this lemma. So it's a count in some sense, and we will do this by induction of the number of edges that have flow on them. So if no edges carry flow in the base case, so this done by induction, we always have to think about the base case. If there is no flow on any edges, then there are also no edge disjoint paths, cannot be. Also, if the value of the flow is 0, what that means is that there is no path from source to sink. So that means that there is also no flow. There is no flow. That means that there can also be no edge disjoint paths. Okay, so we will now compute a path from source to sink. and define a new flow. So on our path, we will actually reduce the flow. So we will go from the flow f to the flow f prime. So the new flow has actually fewer edges that carry flow, and actually also a lower value, f capital F minus 1. So we have subtracted one part. And then actually we can apply the induction hypothesis. The induction hypothesis states that the lemma is true for f minus 1 value or less. So that means that we do have value f minus 1, and the lemma states that then we have f minus 1 edge disjoint paths. Well, we have already one path p plus f minus 1, so we have f disjoint paths. So proof by induction means also in some sense a recursive algorithm. So we will compute paths and actually go to a diminished flow from flow f to flow f prime. Okay, let's prove this lemma by means of an algorithm. So how do we compute a path? Well, there is positive flow, otherwise we are in the base case and our recursion stops. So we have a vertex that is connected to the sink and for which there is flow. So we define then a new flow by setting the flow to 0, f prime for that edge is 0, and we have the start of our path. Now, if that vertex u was to sink, then we're done. Otherwise, we apply the conservation condition. So we have a flow of 1 that went into u. Then by conservation in this flow network, we actually also have to have a flow out. So there is another vertex v, and for which there is the v is connected to u, and there is a flow. So we computed, we ran the Ford-Fulkerson algorithm, and we found the flow. So we're going to define the new flow as 0, and then add this edge uv to the path. Again, if the v is the sink, then we stop. Otherwise, we continue. So this is a iterative algorithm with a goto. Okay, this is actually a lecture and a chapter on iterative algorithms. Does this terminate? What would happen if we have cycles in our graph? So also our path, we would return to the same vertex. So the proof of the lemma stops here if we have a path and it ended at the sink. But what if you reach the same vertex? Can that happen? Well, so that's definitely problematic because we have an infinite loop. Well, what you can say, look, if you have a cycle, then all the vertices that you have already traveled on, you go back and you set them all to 0. That's actually the short way. The longer way, a little bit more efficient practical algorithm, you would initialize your new flow f prime to f, and then start modifying the f prime, which would mean that if you would visit v again, you came first to that vertex v from u, but actually you put the flow on u to v in the new flow, you set it to 0. So if you're looking for paths that carry, if you follow edges that carry flow, then because you set it to 0, if you come again to that same vertex v, which can still happen, then it should have been from another vertex. And you continue this reasoning. So the next time you would come to that same vertex v, it would have to have been from another vertex other than u, other than w. So you can come back at most n minus 1 times. So this algorithm then would actually stop. In that case, if you really would have set everything to 0, then you would have had only one path. Um, but the point is that this is a well-defined algorithm. So the reasoning here that I'm using in the proof of the lemma also defines the algorithm to compute your paths given the flow. Okay, so it is an algorithm. How many steps do you actually need to do? It's important that it is linear. Is it linear now in n or is it linear in m? And justify your bound. So just like we are running an algorithm, we are computing a value, the number of edge disjoint paths, but the algorithm lists as well all the different edge disjoint paths in the same time. Okay, let's now look at the running time. So in general, the Ford-Fulkerson algorithm runs in time that is the product of the number of edges and the cost bound computed by the sum of the capacities of everything that comes out of the source. So that is a upper bound that you can compute on the maximum flow. You cannot compute a flow that's larger than that. Now here, so the m times c, the capital C depends on the size of the numbers. And we've seen that there could be a problem with the original Ford-Fulkerson algorithm that you really have to do capital C number of steps, which can be quite long. So unfortunately for this problem, we actually know that the maximum flow is actually, for this case, bounded by the number of vertices. That's why you can replace the capital C by the little n. And actually we can solve this edge disjoint paths problem in strongly polynomial time. So in some sense, the algorithm, it's the same algorithm, but it will run for sure in strongly polynomial time. So we said when we had the capital C there, if an algorithm is polynomial time, does a polynomial number of steps, but the number of steps may depend on the size of the numbers of the input, then it's not strongly polynomial, but we talk about pseudo polynomial time. Okay, so we actually have also a result from graph theory, which I state here. Um, and this can be derived by the maximum flow minimum cut theorem. So when we worked on when we discussed the Ford-Fulkerson algorithm, we said that the Ford-Fulkerson algorithm not only computes maximum flow, but also computes the minimum cut. And Menger's theorem says that the maximum number of edge disjoint paths from any two nodes equals the smallest number of edges that you need to cut in order to separate those two nodes. Now, perhaps to us now it seems very straightforward because we have studied the minimum cut. But at the time, and this theorem was proven before the Ford-Fulkerson algorithm, that was a non-trivial result and still important thing in graph theory. And it's similar to when we considered the bipartite matching algorithm in the previous lecture that we also can solve. So the largest number of matchings in a bipartite graph, think about the job assignment problem. Finding a certificate was actually Hall's theorem. Now, Hall's theorem can actually be derived, made very constructive with Ford-Fulkerson. So the algorithms that we compute, we are interested in numbers, so the maximum value of a flow, the maximum number of edge disjoint paths, but studying what the algorithm actually does, we compute a lot more. not only the maximum flow, but the minimum cut. Not only that number, but also all the edge disjoint paths. Okay, so this is our first problem, first application. Well, it's our third application, but the first application in this lecture. The second application is an entire different problem, but it can be solved by the same algorithm. So here is the survey design context. So we have a number of products, Q, and we have a number of customers, K. And we also know the history. So which consumer bought what product. So we want to design a survey. So obviously, if a customer has not bought a particular product, then we will not ask questions to that consumer. Also, I should say that this is a natural example of a bipartite graph. On one side, we have the consumers, on the other side, we have the products, and we will have edges between consumers and products if the consumer has bought a product. Now, we have a lower bound on the number of questions that we can ask a consumer, and also an upper bound. So we want to involve all our consumers. So I think a natural lower bound is at least one. And because every consumer bought at least one product, one is a natural lower bound. But also there might be a natural upper bound, and that would be the number of products that the consumer purchased. Now, similarly for a product, we have preferences. Actually, no, I'm sorry. Every product needs to receive a number of questions. So we would assume that every product is at least purchased by at least one consumer. And also, there would also be a natural upper bound on the number of questions that we need from for that product. Okay, I hope this problem statement is clear. So here is the survey design problem a little bit stated more formally. We have K consumers, here on the example 8 values for in the set A. We have 6 products, and the edges indicate which consumer has bought what product. We want to decide, it's actually a feasibility problem. Can we actually ask how many product questions between certain ranges? And actually, can we receive also for every product a number of replies? Okay, so this translates into a flow problem. So here is the circulation problem pictured in the abstract. So we need one source, call it always S. And then we have for every source, we have only one source. For every customer, we have one edge, and the edge has upper bound capacities to the number of questions you can ask that customer, and a lower bound on the least number of questions that you can ask. Then the capacities on the edges between customers and products is 1, and the lower bound is 0, but if you write 0, then it means that the customer didn't purchase this product. And then we have the product, the replies for the product, which will be directed to the sink. And it is a circulation problem. We add up all the upper bounds for the customer questions and all the lower bounds. And that is circled back to the source. So you can see that there is conservation here. So this is obvious for the sums of all the upper bounds, the sums of all the lower bounds, follows immediately from the notation. Now, obviously, if you have a survey, then the total number of questions also equals the total number of replies that you will receive. So that's the other. So the question is actually, can you define a flow that realizes this circulation? So it's a circulation problem with upper and lower bounds. In the previous lecture, we showed that a circulation problem with upper and lower bounds can be reduced to one with only upper bounds. We can modify the network. Okay, a numerical example, please. Um, use the picture, the abstract picture on the previous slide, along with the graph shown, and there's still a typo here. I meant not slide 4, but actually this should be slide 16. So you have 6 products, 8 consumers. Draw actually for that the network. So you have one source, and you have the limitations that every consumer should have at least one question and no more than 3 questions. The same lower and upper bound. And then for every product, you must have at least 2 replies and no more than 3 questions. So these are the upper and lower bounds. Is there actually a feasible solution? So you can try to think that 8 times 3 and 6 times 3, they're actually different. So that might be a problem, but there are the values that matter. So you can already see if these intervals, the sums of the intervals, if they allow for somehow a circulation that can be found. Now, this problem is a puzzle, and you may be able to solve it without running the algorithm, but run the Ford-Fulkerson algorithm to compute a flow on this problem. Okay, let's now consider the algorithm for the survey design problem. We are given a bipartite graph, and the lower and the upper bounds on the questions for the consumer, and also the customer replies on each product. And we define a new graph, which is now a flow network G prime. And in the terminology of the previous lecture, where we worked with supply and demand, here actually we do have that all the demands are 0. Okay, the construction of the flow network is given by an algorithm, and we do have an algorithm to solve that flow problem. Now, of course, it would be, and that's a polynomial time algorithm. Now, it would be terrible if, say, the construction of the input would actually be not polynomial. So what is the bound on the running time to construct the flow network G prime? So you're going to add a source and a sink. So you're going to add as many edges as you have consumers. You're going to put flow on those. You're going to define capacities, upper bounds and lower bounds on all the edges that you have. So the algorithm will be at least proportional to the number of edges you have in the bipartite graph, but you will visit every edge in the bipartite graph only once. And it's also depending on the total number of edges, which is k plus q, because that's the number of edges that you add And k plus q is actually the total number of edges, n. So it's linear in the graph, in the size of the original graph. So that's the point here. Okay, now again, we do have an algorithm. We actually have two algorithms to formulate the new input to construct the flow network. And we have the Ford-Fulkerson algorithm. But the important problem is, of course, does the maximal flow correspond to a feasible circulation? And if we have a feasible circulation, what does that mean in terms of the survey design? Okay, so feasible circulation that can be computed by the maximal flow. And here this is interpreted with the flow with the lower bounds. We've seen that this actually translates then into a network that has no lower bounds. Okay, so we have two directions. If we have a feasible solution, then we have an integer valued solutions for the integer demands, the capacities, and the lower bounds. So here we have that any integer value circulation corresponds to a survey design. So these are the number of questions that we have asking the consumer and the number of replies every product will receive. Okay, so there is a natural correspondence from a circulation to a design. Now, if you have a design for the survey, how can we turn this into a flow? Well, if for every question a consumer is asked, we have flow. Otherwise, there is no flow, so it's actually a 0 or a 1. So, but it's adding up. So if a consumer is asked so many questions, then there will be a flow of that value. And the same for the number of replies of the customers that go about the product. So what flows into the sink represents the total number of questions. And coming from the Jade product, that's the number of replies that the product receives. So the total number of questions will be the flow going from sink to source in this circulation. And now what do we have? We have a survey in between the lower and upper bound number of product questions that we can ask every consumer. And we will also have something that is satisfying the constraints on the consumer implies. So all the capacity conditions are satisfied, and the demand of actually every node in the terminology of the previous lecture, every node in this flow network with demands, the circulation with demand problems is actually 0. What goes in goes out. So that terminates the proof. So we solve our survey design question by the circulation with demands and lower bounds problem, a problem that we considered in the previous lecture. Okay, what is now the upper bound on the running time? So we have all the inputs. So we have the k consumers, q products. So k plus q vertices in the graph. We have probably many more edges, depending on which product was bought by what consumer. Then we have the bounds on these number of questions that we can ask. We have the running time of the Ford-Fulkerson algorithm, which is m for the number of edges in our bipartite graph G, plus essentially the number of, so the total number of edges in our flow network. So the M here, the M that you use in Ford-Fulkerson is actually the M of the original bipartite graph plus the added edges is K plus Q. So you have the M plus K plus Q times the value of the maximum flow, or here actually the sum of all these demands. No, the sum of all the questions that you have, because we have zero demands. Now, uh, the algorithm may or may not depend on these lower and the upper bounds. So that's for you to figure out. So you will reduce this, you will actually get rid of all the lower bounds, uh, but then you still have to decide on the value of the maximum flow. And this can still be quite depending on the values of the numbers. So I would say that the problem would not be solved in strongly polynomial time, unlike the first problem we considered with the edge-disjoint paths problem. Okay, this concludes the first half of the lecture, the last lecture that we spent on network flow or on iterative algorithms. So we considered two very distinct problems, and one of them can be solved in strongly polynomial time by the Ford-Fulkerson algorithm. The other problem was entirely different, and that problem, to fully understand it, refers back to what we covered in the previous lecture, but there we have that we don't really have a strongly polynomial time algorithm. Okay, we continue with our last application of the Ford-Fulkerson algorithm, and that is once again a scheduling problem. And since this is a summer course, we all travel, it is an airline scheduling problem. And it's very good that this can be done in polynomial time.